from Frankfurt University on 2009. And from 2010 and 2012, she was a postdoc and a visiting assistant professor at Duke University. Since 2013, she is a Fairs Fellow and professor at Frankfurt University. And since 2018, she also leads the group of transport and experimental simulations at the GSI. She actually did many excellent work on relativistic heavy-ion collisions and QGP, such as developing an integrated Boltzmann hydrodynamic approach, studying the initial state fluctuation and the final state correlations, dynamical description for heavy-ion reactions at the fair, and so on. Today, she will review the recent progress on SMASH. Please, Hannah.
Thank you very much for the kind introduction. I'm very happy to be invited to the seminar series, which was originally planned as a workshop. Unfortunately, couldn't take place as many of those this sort this year. And I'm happy to present you today what we did so far with our model SMASH. And if you have never heard this acronym, it will become clear in a minute or two. But let me get started with with a more general introduction, because this is a seminar about the beam energy scan energies, and I'm not having much results directly related for the experiments in that region, but we're moving towards there, and the main goals, as we know in our field, are to understand the relevant degrees of freedom at high densities in this case, but of course also at high temperatures. And as we are usually studying in our experiments, like here's a picture of star at the relativistic heavy ion collider, and here's a picture where the beam energy scan program is indicated. Of course, we have no clue if this location of the phase transition and the critical endpoint is actually true. So this is one of the big, would be one of the big landmarks to identify that. And this effort has also the connection to the neutron stars, and in particular neutron star mergers, as they have been recently observed, and one can actually study. I mean, we're actually studying the same type of matter to a certain degree, I mean, apart from symmetry energies, in our laboratories. So this phase diagram, if you look at it from the theoretical modeling perspective, has two ends. So at the high energies where Rick and LHC are exploring the physics at high temperature, we have established in our community some kind of standard approach of non-equilibrium initial evolution, then viscous hydrodynamics, and then coupled to hadronic rescattering in the final stages. And that model works very well and is just refined and established, and of course there are still details to be figured out, but the major parts of the model have been identified, and it works rather well. And many people actually use these type of approaches and move down in the phase diagram to see how far one can push these hybrid approaches. And I'll also touch this a little bit later on. But the main part of the talk will be coming from the different directions. So one can also do the opposite and start at the high density, low temperature regime here, where also since many, many years, there are hadronic transport approaches that I've used to describe the dynamical evolution of heavy ion collisions. And there you are relying on resonance dynamics and nuclear potentials, depending on where you are in this density regime. And again, I've listed here some of the overall arching goals of what we would like to achieve in the future. So one is, for example, the constraint on the equation of state of nuclear matter, which is particularly helpful in the connection to the astrophysics community. But also one of the ideas in developing a new transport approach, and here again the name SMASH appears already, so this is a hadronic transport approach that we developed in the last few years, is to see where this is still valid and where a description in terms of hadrons is still okay, and at which stage we are moving into a different state of matter and where we have to have the quark and gluons degrees of freedom. And so to also set the stage a little bit, I wanted to show again these nice pictures that we have produced also now already almost 10 years ago, but still I think they are very, very nice to illustrate the point. So we are not sitting at a certain single point or on a single trajectory in this phase diagram, but actually our collisions, this is for 40 GeV lab energy, so 8.8 square root of S. You have a whole blob in your hydrodynamic evolution in this plane, and if you look at the later time, that moves downwards. So for any detailed dynamical modeling, one needs the equation of state in the whole plane, as you can imagine, and one needs also transport coefficients and their dependencies in the whole phase diagram, which is rather challenging in the end, if you really want to include all these different things. And of course, eventually one wants to also cope with the non-equilibrium dynamics at the phase transition. Also, just to have a nice intuitive picture of this, let me show here this animation where on the left-hand side you can see the hydrodynamic evolution in space. So you just see in the z direction how this volume or how the system expands. And on the right-hand side, you see the same system mapped on this phase diagram. So this is the dynamic picture to what I've been showing statically before. So you get some idea on where our system is moving in some intermediate energy range. Also, we tried at some point to make some more quantitative pictures of where one is in the phase diagram at different beam energies. So this is a whole set of beam energies that are, some are already covered, some will be covered in the beam energy scan. And that was using, so these pictures are using the UQMD hybrid approach at that time. And you see basically the mean and the variance of the temperatures and barochemical potentials on the freeze-out hypersurface. And what I wanted to illustrate here as well is if you change centrality, this is, for example, here these pink points are different centralities at one beam energy, you end up at very different positions here. Then the left is for one certain, for the chiral equation of state, the right-hand side indicates the same picture if you use a hadron equation of state. So these values that we're used to talk about with temperatures and chemical potentials are highly dependent, of course, on your equation of state. The actual physics is encoded in the density, so in the energy density that you actually propagate in your hydrodynamic evolution. But nevertheless, it gives us some idea on which, where roughly we can, well, I think the main takeaway so far is that with heavy ion collisions, we can really span this phase diagram rather extensively, and we can really look into this, into those details, and hopefully really find out something about the features in the phase diagram. So then I have my advertisement slide also right in the beginning, where hopefully many of you are still awake. So this is the current picture of the FAIR construction site next to the GSI campus in Darmstadt. So here you see the current GSI facility, and you see the big construction site where the major part here, this north area, has been started probably roughly 2 or 3 years ago, where they started really the digging of the tunnel. And now they are, I think, almost completed with the tunnel and almost already filling it up again. And I think over here is the cave for the CBM experiment, which is the compressed baryonic matter experiment, which is the one that is most relevant for the physics we are interested in, where they will shoot with very high luminosities gold beams at a gold target up to 11 GeV. And this is on the right-hand side a small visualization to give you some idea on how this is going to look like if one visits that in a couple of years from now from the outside. So there's some nice greenery planned around that. And yeah, so nevertheless, this is just what's going to happen very close by to where I am right now. And now I'm coming to the actual outline. So I hope I motivated why one needs then dynamical models for this description of the heavy ion collision in this intermediate range. And we developed this new hadronic transport approach called SMASH, and that's what I'm going to cover today. So I'll tell you about the ingredients and a little bit about how to validate such an approach. Then I will start with the particle production at CIS-18, so the current GSI facility accelerator, because this is basically where you expect the hadronic transport approach to work rather well. And then I have some results on Barron's topic and the very recent developments of a hybrid approach based on SMASH. And I have a little chapter on electromagnetic probes, and then I will cover transport coefficients because they are of interest because they encode the properties of the strongly interacting matter that we are studying. And we have looked at quite a few of them in the recent 2-3 years. And so here we will talk about shear viscosity, bulk viscosity, and the so-called cross conductivities. And in the end, if I still have time, I have some next steps and outlook so you get an idea where we are moving with our approach. So let's get started. And first, again, let me motivate why we have developed a new approach, because one, they are successful in some domain for the dynamical evolution in the heavy ion collision. Also, they are really, in a sense, universal, because you have to, and at very low energies, the whole evolution is covered by your hadronic transport, whereas at high energies, you use the exact same model with the same cross sections, the same particles for the late stage rescattering. So also at RIC at LHC, you will need eventually a hadronic transport approach that has all this, these details in there that are in best of all cases then benchmarked against the low energy results. And yeah, so there has been also new experimental data. If one looks at the PDG book from time to time, there's actually always updates, especially concerning resonance properties and some of the basic cross sections that one needs and so on. So in our philosophy, we try to build a very flexible modular approach, which somewhat condenses knowledge from the existing approaches. So of course, there have been approaches before in the literature and that are still developed actively. But we were trying to basically pick the best solutions from these approaches to put it in one approach and to adapt it to the newly available data as much as we can. And then the physics motivation, again, is to have a baseline calculation where you have hadronic vacuum properties, and then one can see any deviations from that tell us something about more interesting physics. And sometimes the baseline by itself is already interesting. So here's the, so this is the approach. So SMESH stands for simulating many accelerated, strongly interacting hadrons. We include mesons and baryons up to roughly 2 GeV in mass. I have a list later on in a few slides from now. We use a geometric collision criterion, and we have mainly binary interactions. So we have inelastic collisions through resonances and string excitation and decay. And yeah, and if you are interested, and I have a whole list at the end, but this is the main web page to get all information you might need about the approach. And just to also say something about the picture I'm showing here. So this is a heavy ion collision, a gold-gold collision at very low beam energies. So this is why the nuclei are still almost round. And what we did here is to coarse grain the evolution, and you actually see an energy density for the nuclei and their Landau frame velocities. So you have here these velocity arrows. And the main point is to indicate that also here you build some high density region in the middle of the system, and then you also develop collective flow as we're used to. So you develop this kind of flow structure and these low energy collisions. And for us, this was mainly to see that the approach somewhat does what it should do. So this picture demonstrates that this describes the what one can actually simulate here the dynamics of heavy ion collisions. And no, okay. And now I'm also have to tell you that I'm not doing that completely alone, and the current list of people in my group is basically here on the left. And then we have a few people from the outside who were at some point in the group or just externally through different projects. And this is a picture recently in Frankfurt, so you also get a little bit the skyline view, where we did a social distanced group event where we went on stand-up paddle boards. So we were only that close to each other during the picture. Apart from that, we were always at least 2 meters apart. So then we have here the general setup of the approach. So what do you do in such a transport approach? You solve the Boltzmann equation, the relativistic Boltzmann equation. So you have a single particle distribution function that you represent by individual particle degrees of freedom. And then we have here this free streaming term, basically, and here you have the nuclear potentials or the forces from the nuclear potentials. And on the right-hand side, you have the collision term that gets increasingly complex if you have many different species interacting with each other. Yeah, then here we have our collision criterion. So we calculate the transverse distance between particles, and if that distance is smaller than the total cross-section, here in this aerial definition, then these particles collide. Then sometimes in some cases one also needs to use test particles, which basically implies that you scale the cross-section down and increase the number of particles, and so you don't have 1 particle per real particle anymore, but maybe 20 or something like that. And the collision criterion is exactly the same as has been used in other approaches, for example, in your QMD. Then you have to have some initial condition, that is your nucleus, where we basically sample according to a Woods-Jackson distribution. That the sampling is successful is shown in this left-hand side picture, and this is maybe not so exciting, but what I find a bit more interesting is on the right-hand side, this little movie that hopefully plays now, where you can see that we're actually able to simulate a nucleus that is actually sitting where it should sit, with the potentials turned on and the Fermi motion, so they actually kind of stay together, and at least they are staying long enough together for the purposes of heavy ion reactions. So you see this simulation runs until 200 Fermi. We don't need the nuclei to stay together that long, because before they will have collided. We also have the possibility to initialize deformed nuclei, and we can also freeze the Fermi motion. So for higher energy collisions, the potentials are not that important anymore, and then one uses something like that is called the frozen Fermi approximation. So you just have the Fermi motion included, and your nucleus still doesn't fly apart, because you don't take that into account when you propagate the particles. And then we have another feature that we actually explored in this work, where we just read in the positions for the nucleons in the initial nuclei from an external file that was then generated with knowledge about the nuclear-nucleon interactions by Massimiliano Alveoli and Mark Strickman, so based on actual theory input. And that then includes also the neutron skin, for example, or correlations between the nucleons. In our default setup, this is all not there, but if you read in these external files, then this can be included, and we show here on the left-hand side. So this is this neutron skin effect that is basically telling us that in some neutron-rich nuclei, the neutrons prefer to sit on the outside. So this is the ratio of the proton over the neutron distribution. So this goes down if you include this neutron skin. So then you have basically the proton sitting more on the inside of your nucleus and the neutrons more on the outside. This is why it's called neutron skin. And why did we look into this? Because we are suspecting that this has an impact on the isobar run that was carried out at RIC, where ruthenium and zirconium were collided, in the hope that you have just the difference in the different charge number that makes you a very different magnetic field. But since only one of those nuclei will most likely have a neutron skin, and here we have the most pessimistic basically assumption, so the largest neutron skin possible for zirconium assumed, but in that kind of worst case scenario, you will change the difference in magnetic fields here by roughly 50%. So you will not see as much difference in the magnetic field as one hoped for. Yeah, so that was one application of our initial state implementation. And then I promised the list of degrees of freedom. So this, of course, is also a little bit adapting over time and changing over time. But I think at the moment this list has been stable for a year or so by now. So we have quite a bunch of resonances, and in particular in the mesonic sector. Also, this is much more extensive list than in the OQMD approach, for example. And yeah, so that is basically to match the current particle data group idea, what is currently in the particle data book. And of course, if I'm listing here a particle, that also means that the corresponding antiparticle is there and the whole isospin multiplet is included. Yeah, we have then also in most cases isospin symmetry assumed to have some possibilities to cope with all these interactions. Then I have this one word about how we treat resonances. So our resonances have relativistic Breit-Wigner spectral functions, so no explicit medium modifications due to the width or so. And we have particles with very small width. We decide to be stable, so we only treat the strong decays, no weak decays in our approach. And for then there are different ways how you can treat with the mass-dependent width. So a higher mass resonance will be more likely to decay than a lower mass resonance because more channels are open and more phase space is available. And this we encoded with this framework suggested by Mandey and Zaleski. And this is actually the treatment that has been chosen in the decent BOU transport approach, and that was very successful. So we followed that way here. So now we have all the ingredients, and to now show you some of the basic checks one has to do with such an approach. We have here the elementary cross sections. That's of course the first step. And now you could say, oh, this is easy because the cross sections are anyhow parameterized. And that is not true. As you can see here, for example, in the peak-P cross-section, one can nicely see that the elastic cross-section is parameterized, so that is no wonder that this line fits. But here in the total cross-section, you see this funny shape. And the funny shape appears because we have some different channels that contribute to that cross-section. So we basically have all these different channels and have input for all the different channels, and then the sum has to correspond to the data points for the total cross-section. In the proton-pion case, this works pretty well. So we reproduce all these peaks here by the different resonance contributions. And this is not a single resonance each, as you have seen in the list before. There's a whole bunch of different states. And online, you can see all these different plots with all the, I don't know how many channels that are contributing. I just chose here the bit more cleaned up versions to see what's going on. And also what you can see from these pictures is that this there's a line at low energies, which is the resonance cross-section here, for example, and this is going down at some point, and then there's this blue line appearing, which is the string processes. So this is what we call soft strings. I will later on come to this, what is soft and hard strings in more detail, but this is then the transition to the string excitation regime, basically. So this is one of our basic checks that we reproduce still the elementary cross-sections. And also let me note that all of what I'm showing here, we basically check again for each new public version. So we have roughly every half year a new public version of the code online, and always for every of such versions, we are checking a whole different thing, a whole bunch of results, and beyond those results are these cross sections. So one can really follow if something changed, where it changed and why, and what change was responsible for it. And another basic thing is the detailed balance, which is the reason why we chose in the beginning to only include 1 to 2 and 2 to 2 processes, because for those we can implement detailed balance. So you have the forward and backward reactions, and you count the forward backward reactions. And if this line here agrees, then everything is fine. And then we did also another check, which was possible because some colleagues here calculated an analytic solution of the Boltzmann equation within an expanding metric. So we actually were able to have also an expanding sphere scenario, which we could adapt to that metric. And you can see with our data points here, we actually matching, so the points are the smash calculation and the lines are the analytical values for the densities in the time evolution. And here you can see the full distribution function as a ratio to the equilibrium distribution function. And also that test was passed very successfully, and it actually proves that the implementation of the collision algorithm is okay. Then there is a more extensive comparison effort between different transport codes, mainly applied at really low beam energies. And this is one paper that has been recently put together, but there's another one even now on the delta nucleon pion system. So this is a continuing effort since a few years, and we joined it as soon as our approach was able to compete with the features. And that was basically just really looking into all the details that you have in these transport approaches and compare how they are performing with respect to each other and identifying how the codes look like. And yeah, so this is for me also part of the validation effort. And then we can finally come to the physics. So I'll start with the particle production at low beam energies to just benchmark the approach in the first place. So in the first particle species we look at is the pion production. And this is here on the left is the excitation function in gold-gold collisions. And this is data from the FOPI collaboration at different beam energies. So this is really very low beam energies. And here you can see the difference between the so-called cascade approach, which is the red line, which is what you would probably use at high energies if you would run a transport approach That means that you don't include nuclear potentials and you just have the collision term. And then with test particles, not much changes, as it shouldn't. And then if you include potentials, the pion production is a bit reduced, which is also what other approaches are seeing. And then with Fermi motion, you put more energy into the system, so you're able to produce more particles. And Pauli blocking reduces this a little bit again, also as some collisions just cannot happen due to that. But Pauli blocking is also only relevant at very low beam energies. And these other two plots, as far as I remember, actually not gold-gold. I think they're carbon-carbon or something like that. But here you see the pion production in the transverse mass, and we are doing not such a bad job in describing this pion production in these small systems, at least. And then I would like to move on to the more collective behavior. So now I mentioned these potentials quite a few times. So this is what we currently have for the nucleon interactions. We have a basic Skirm form for the potentials as parameterized here as a function of the density with 3 parameters, alpha, beta, and tau. And depending on the value of these parameters, one can include an interaction that basically corresponds to a so-called soft or hard equation of state. I just give these values here because some people call hard and soft some different things. So I'm going to call it like this in this presentation. And there's, of course, also some symmetry potential to encode the isospin difference between neutrons and protons. And here to show side by side a comparison to prior UQMD results, here we have the V2 excitation function and at low energies. So this is the elliptic flow for charged for protons. It's actually charged particles, but at low energies, it's mainly protons. And so this full line is the cascade approach, which you see matches the data roughly around here at high energies. Of course, a transport approach doesn't have enough flow. We know we need hydrodynamics here in this region. And at low energies, one actually needs these nuclear mean field potentials. This is where this dashed line comes in. And in essence, what we have done here on the right-hand side, this is the SMASH result. The red line is also employing a similarly hard equation of state to the UQMD result over there. And the same data points just displayed a little different. And one can see that at these low energies, this hard equation of state gives a good description for the V2 excitation function. Now, what we can also do and what we're currently working on is to look at the particles in the light clusters, so to say. So the deuterons, for example, so the light clusters have some quite some interest in the community. And so we had here in this seminar series, Dima Olinichenko gave a talk a few weeks ago on this topic. So I don't want to repeat the whole story here, but he implemented some mechanism to microscopically produce deuterons in our SMASH transport approach. And he applied it for final state rescattering at high energies. Now recently he put a paper out also on the beam energy scan with that approach. Here we apply this microscopic mechanism to produce deuterons to low beam energies. So this is compared to the hardest data on deuterons. For here, this is V1 as a function of PT, and the other plot is V2 as a function of rapidity. And also there, the hard equation of state gives us the best description of the data. So one always needs, one is sensitive to these potentials and needs those potentials to describe here the collective behavior in low energy collisions. Then one cannot only produce pions or deuterons, but we can also produce strange particles. And the easiest to produce are the kaons, but also there, of course, the production mechanisms are rather different. So the K plus is much easier to produce because you can produce it together with a hyperon directly from a resonance decay, whereas for the K minus, you always need to produce the corresponding antiparticles. So you will have a higher threshold, so it's more complicated to produce K minus basically. Nevertheless, so there are these production chains and lots of different cross sections, lots of different resonances with their properties that are barely known in many cases. So what we did is a big effort to compare to exclusive production data for different strangeness production channels, and then actually see can see all these many little contributions that in the end have to add up to produce the proper strangeness fields. To compare this with, I mean, if you make this comparison to current heavy ion data, turns out that actually even with matching the elementary cross sections, we are not, so we're basically over predicting strangeness already in the transport approach in the low energy collisions. But yeah, so that there is still some ambiguities that have to be tackled further, but at least we have some start on it. And we also made with our current setup predictions for the most recent system that has been measured by the hardest collaboration at GSI in spring 2019. So this was silver at 1.58 GeV, and we have looked here at the like this effective slope of the spectra of the final particles that are produced, and one gets for the different stage particles something on the order of 90 to 100 MeV, which makes some sense. And then also we have looked at the multiplicity and at the system size dependence of the strangeness production. So this is for 4 different systems and different centralities in these 4 different systems. And then one can make this overall qualitative fit to these strangeness production data, which was also done by the hardest experiment. And even though the absolute values don't really match these fit parameters and so the shape of the curve, so the qualitative dependence on the system size looks very similar. So now that we have looked at the low beam energy hadron production, we wanted to move to higher energies. And then one needs to actually include these string excitation and fragmentations. And this is why I zoom in here again on this cross-section that I've been showing before. This is the proton-pion cross-section once more. So here we have the resonance region, and then we have the soft strings. The elastic is somewhere here, this green line. And then you can see that from 10 GeV on, it is possible to call Pythia for the hard scattering. So this is then where we basically just directly call Pythia, and Pythia handles the whole hard scattering process and only gives back the hadrons to us. And for the soft string part, we excite the strings ourselves and only hand over to Pythia for the fragmentation. Yeah, for the full treatment by Pythia, the disadvantage is that Pythia only can cope with pions and nucleons. We have, of course, many more different particle species, so we have to map all of those onto pions and nucleons, and hope that things are universal enough to do that. I also would like to make a note: in our next release, which will hopefully come this fall, we will include optimized Pythia calls. So if anybody is interested in running our approach at high energies, I would recommend to wait until this version is there, because it will vastly reduce the runtime. So from actual hours, it will reduce it to minutes or seconds. So this made a huge difference, and we had to wait for some internal Pythia restructuring to happen, and now this has happened, and we have actually adapted our code so we can use that new version of Pythia, and that made a huge difference. So it's really actually usable for high energies now. Yeah, and then with this applying now this string excitation and fragmentation, we can study heavy ion collisions at higher energies. And what we did, because there are again a lot of parameters in the string model, we tuned that to elementary data from PP collisions at SPS, and then we calculated LED and looked at a comparison to experimental data, and the result is here. So it's a bit cluttered, but nevertheless, hopefully it's visible that from lower energies, which is the blue line, to the purple line, we have a description of the Gaussian shape to the double peak shape at high energies of the proton dn dy. That has been also observed in the data, and matching of the data is not perfect, but it's certainly okay. And this is also compared to the dashed lines here, which show the result if you use the public QQMD version in the same setting. And the goal of this high energy running was also to be able to use SMASH as an initial state for a hydroevolution. So this is, for example, the density distribution at a square root S17 GeV collision in a central collision. So this is a typical picture of a fluctuating density distribution that you could now plug into your favorite hydro approach, and actually plugged it into our favorite hydro approach, which is the VHLLE code from Yuri Karpenko that was also employed in this study in 2015, where we sandwiched this with the UQMD initial state and then the UQMD final state. We have basically achieved the same full event by event hybrid approach based on the SMASH initial state with the SMASH final state. And we use, in this case, a shear viscosity over entropy ratio of 0.2 as it came out from this study over here in this energy range. So this first preliminary calculation I'm showing here is for 8.8 GeV lead-lead collisions, and we see here this is the pions compared to the data and the kaons, and on the right-hand side you see the protons. And we're of course working on this at this point and try to improve the different missing links, and also of course compare to other equations of state. At this point, we have just included this chiral equation of state that was also used in this prior work here, and match it to the SMASH equation of state in the final time step. Talking about equation of state, since this is something that many people need to do if you eventually want to run with SMASH as a afterburner or for your final state evolution, you will always need the proper hadronic equation of state with these right degrees of freedom. And for that purpose, we are also going to provide parametrization and tables for this equation of state that is coming from the SMASH degrees of freedom. And I'm showing here the full lines are our equation of state results compared to the lattice data. And in the low temperature region where it should be similar, they are more or less similar. And another point of importance is that if you're at finite mu b, you certainly need a mu b dependence, this is clear, but you also will need a mu q dependence and a mu s dependence, because these values here give you some idea on how large these chemical potentials are if you're on a freeze-out hypersurface in these 10 square root S10 GeV collisions. So there are some significant values for these different chemical potentials, and one needs actually a 4D table and parametrization that we will provide in the near future. So now let's get to the electromagnetic probes. So we also can not only produce hadrons, but we can also produce dileptons and photons. And the dileptons in our approach are mainly produced by resonance decays. So there are some direct decays, then there are these Dalitz decays, so three-body final states. And we are using a method that's called the shining method. So you basically always, if there is a row in the simulation and it decays, then it will not only if it decays, but if there is a row in the simulation, it will always emit dileptons all the time, and not only when it once decays. And that basically is then weighted in the end by the proper probabilities to increase the statistics, because otherwise the electromagnetic processes are too rare to really treat them directly in the code. And yeah, so what we did for the dileptons is to also gauge our model in elementary collisions. So we looked here in the proton-proton data from HARDES at 3.5 GeV, and the black line is our calculation, and it actually nicely matches the experimental data. And yeah, one comment to make is that on the left here, I'm plotting the dilepton emission from the rho and the omega and the phi. And we also have emission here or we have a width at below the pion mass. So actually our resonances can also decay to dileptons down to the leptonic threshold and not only to the hadronic threshold. And also again, here is a side-by-side comparison between the SMASH and the UQMD results. So this is in carbon-carbon collisions compared to the HARDES data. And yeah, we do a rather decent job there with our tuned setup to elementary collisions. So with what we did for proton-proton, we just apply it now to the small system carbon-carbon, and it actually looks rather reasonable. Then moving to a larger system, this is Argon KCl, and already there one sees that this dashed line, which is just the contribution from SMASH itself with vacuum spectral functions, doesn't really match the data anymore. So here one already sees explicit medium modifications that we can include at this point only through this called cross-graining approach, where you run many events and then calculate densities and then actually connect it to the full medium modified spectral function. So here on the right-hand side, you see the difference between the spectral function for the rho and the omega as they are in the vacuum transport approach. So this is the full lines. The dashed lines indicate what happens if you have this full medium modified spectral function by Rapp et al. And then you get the black curve here on the left-hand side and match the data again very nicely. And we again recently did this study for silver-silver collisions, because this is what Hades is going to publish hopefully soon. And then we could see, which was interesting, that the black line here, which is the silver-silver result for the invariant mass spectrum, looks rather similar to the gold-gold result, which is this yellow dots here. And silver-silver is significantly smaller than gold-gold, but it was run at a higher energy. So gold-gold was only at 1.2 GeV beam energy. And we suspect that this difference in the system size is compensated by the higher beam energy. And for the dileptons, the spectra are looking very, very similar. And also on the left-hand side, you can see a comparison or to get some idea what densities are reached in these collisions. So at least there's something like 4 times ρ0 that is reached in a sample cell. Also rather high energy densities are reached there already. And there is, so 5 times epsilon 0 is already something like a GeV per Fermi cubed. And in the temperature region, we are here at around 100 MeV of temperature, which is then similar to what one expects in these neutron star mergers, for example. Good, then for photons, we have also included photon production from different scattering processes that can produce photons. And we have benchmarked this photon production in a box. So we have implemented all the individual cross sections for 8 channels. And then we have put this system in a box, fill out the photons, and compared it to the thermal rates that were matching the theory that we put in. So this is basically the benchmark here, that these lines are matching well, and this is here shown below that this is working. So we have actually the proper photons produced from these cross sections. And now, of course, the next interesting part is to apply this framework for the within a hybrid approach at high beam energies to see how the photon production in the late stage, in the late non-equilibrium stage looks like. And for that, we also had to add Bremsstrahlung, which was another bigger effort. But now we're close to having results. And I would like to show you here the first preliminary pictures that I got from Anna and Jean-Francois, basically, that show the production. So here on the left-hand side, you see the photon spectrum from the hydro evolution in black, and then from the late stage evolution. So the light band, or these 2 bands here, are still applying the hydrodynamics down to 100 MeV in temperature. So this one band shows down to 100, and one band down to 120 MeV in temperature. If you would basically have equilibrium emission also in the hadronic stage. The points show, or the symbols are depicting the calculation where you really switch to SMASH, and then also for the photon production, look at the photon production from the non-equilibrium transport. And for Bremsstrahlung, so this is the red contribution, the low PT part matches rather well, whereas at high energies the transport produces a bit less than the hydrodynamics rates. And in the blue curve, there is some also rather big difference here at low PT, and we were wondering why this difference appears. And there we have some suspicion, namely that this is because in the in the chiral Lagrangian, the rho, so the rho meson, which is rather crucial for many of these processes, is stable, so it doesn't have a width. But in our SMASH calculation, it of course has a width, because otherwise our processes don't really work as they should be working for the final state hadronic rescattering. So here you can see the difference it makes to give the rho a width of 150 MeV, which is what it should have, compared to having almost no width, so being almost stable. And that really makes this big difference basically between these two curves, and can actually explain this difference between the two blue results here. So yeah, so I hope that we are having more results along those lines in the near future here. Okay, so then I have the last chapter here of my talk on the transport coefficients, because now that we have a transport code which has all these degrees of freedom and interaction in there, we can also see what we can learn about the different transport coefficients that result from that. And transport coefficients are one of the things that many people are trying to study. This is from a by now almost old white paper. So, but it was still this effort of the field to decrease the knowledge on the transport coefficients, and now we are, I think, even making, the further progress from here, besides acknowledging that the viscosity is small, is now to acknowledge that it also has a temperature dependence, and this is shown on the right-hand side. So this is from a Bayesian analysis, where you then can have this posterior distribution for this transport coefficient as a function of temperature, and there's some newer result coming along very soon from the Jetscape collaboration, who are improving on this type of Bayesian analysis as well. So there is two ways. So one can either have theoretical guidance and input for example, from perturbative QCD on what these transport coefficients should be at very high temperature, for example. And this is where then the prior or these ideas come from on how these temperature dependencies can look like. And what we can do with our transport approach is to look at the low temperature region, because there it should be a hadron gas, and then we can basically look at how the transport coefficients are, what the transport coefficients are at low temperatures, and basically hopefully provide constraints for future efforts to constrain these coefficients in heavy ion collisions. So also, if you need to run your hydrodynamic approach, one needs to have some parameterization, and we can basically constrain one end of the parameterization of the transport coefficient. So for the shear viscosity, there have been prior results, of course. So there was a result from the YQMD approach with applying the Green-Kubo formalism by Nasser Demir and Steffen Bass, which resulted in these black points here as a function of temperature. So they had a result for the hadron gas viscosity, so everything fine. But then a few years later, there was an extraction of eta over S as a function of temperature within the B3D transport approach by Scott Pratt, and this ended up somewhere below here. And the question is, if you have a similar transport approach, why do you have a factor of 5 difference between the shear viscosity that you're extracting? And this was the question, or this was at least my motivation why I said it's important to look into this again with now another new transport approach with our SMASH approach, and have a look what we can tell. And this is what we did. We basically put our particles into a box and applied Green-Kubo. So what we did is to calculate the entropy via the thermodynamics, and the shear viscosity then from these correlation functions. So you calculate the energy momentum tensor and correlate it over time steps. You get something like this, and then one can fit this with an exponential, and that tells you then what your shear viscosity in the system is. And we first started with the simple system where we thought, okay, let's just use pions and the rho meson, and then we can compare to an analytic Chapman-Enskog result for eta as a function of temperature. And that was here, this analytic result is the red line. Our first calculation with the normal lifetime of the rho, we got these black points. And then we were a bit puzzled because we thought that we would have to hit the points, but we didn't. And then we went into the details and to understand why this was not fitting the analytic expectation. And we figured that in these analytic calculations, what is assumed is that the pionic interaction is happening at a point, so that this is a point-like interaction. So the lifetime is not taken into account. In our approach, we really, if two pions meet each other, we form a rho meson. That rho meson propagates for its lifetime, so around a Fermi or so, and then it decays into pions. And for the shear viscosity, that matters because that basically delays the momentum transfer that is relevant for your relaxation and the shear. And so then what we did to prove that is to basically set the lifetime of the rho meson to 0 to reproduce this instant interaction for the pions. And bam, we had our analytic expectation. So that was seemingly the explanation for this difference. Then we went to the full result and basically got these, this black line here for the full smash hadron gas. And it's very close, or it's closest at least to this, to the Demir-Bus result, which is now to the UQMD result, which is displayed here as these red dots, which is also understandable because we're in spirit very similar in implementing all these resonances and having them dynamically excited and so on and so forth. While your previously shown Pratt et al. Result is down here again. And still we wondered why is that down there and how can we understand that? So what we did then to kind of at least get closer to their result is to add a constant elastic cross-section to our full smash. And we basically just added a 10 millibar elastic cross-section just to show the proof or the principle. And actually that brings you down there and basically again has due to this effect that you don't delay the relaxation anymore by your resonance lifetimes, it decreases your shear viscosity. So finally, after this first study on shear viscosity, we're now more thinking that one could actually, if we would know the low temperature shear viscosity from experimental data better, we could actually constrain the properties of our resonances or our transport approach in the end, or constrain our hadronic interactions. So we didn't stop at the shear viscosity, but also calculated the bulk viscosity. And the paper is currently on the archive here. And we also, the bulk viscosity by itself is also very sensitive to the resonances or inelastic collisions, or basically particle number changing processes, which are mainly going via resonances in our case, because this is inherently what allows bulk dynamics. And this is indicated, I mean, again, left-hand side indicates a baseline check to analytic calculations where possible, a simplified system. The right-hand side is again a simplified system, but with this is the correlation function now for the bulk viscosity, just to show you the vast difference it makes if you have different lifetime assumptions. So this is basically this stable rho scenario here. So you have this almost no relaxation at all. So you have almost no bulk viscosity really that you can talk about. And then if you go back to the usual lifetime of the rho, you get a very different correlation function, very different bulk viscosity. So these are really factors of 10, 20, even 100 yeah, so this makes a huge difference here. And another thing that was also very interesting that we realized is that in the full hadron gas, when we were plotting the correlation functions, we were not really seeing one exponential anymore, but rather something like this, where you have the impression that it's actually 2 or more exponentials. And then we went back and looked at it in more detail. This is now, again, a simplified system where we have the pi rho system as a basis, and then we included some other particle and another resonance with a very different, so a much longer lifetime than the rho system, basically, just to show what happens in a mixture where you have very different resonances with very different width included. And one can actually, we could actually show in this simplified scenario that the full correlation function is really dominated by this very slow mode at late times, and that basically then also in turn influences the extracted bulk viscosity quite a bit. So in the final result for the bulk viscosity as a function of temperature, we were showing two curves. So we have here this, what we call the full result is here the red curve here, which is rather high compared to other other extractions. And then we also have the so-called smash effective bulk viscosity, which is this green curve here, which is much lower. And what we did to reach this green curve is basically to neglect the slowest mode in our correlation function. So we could fit all correlation functions with like 3 different exponentials, and basically excluding the third, so the long tail exponential, we get this green curve. And that is what is probably more relevant for the heavy ion scenario, because there in the late stage rescattering, these very slow modes don't really have time to play a big role because we have an expansion. So this is our suspicion that or our conclusion here, that this effective bulk viscosity is what one can and should compare to these, for example, here these Bayesian results from these Bayesian analyses, and there we are in the similar ballpark of the results. So finally, let me come to the conductivities. So the first conductivity we looked at was the electric conductivity, so just the response to an electric field in our system. Again, here pion only, very simple system, can match the expectation. Then now let's move on to also study the effect of the lifetime here. And for the electric conductivity, funny enough, we didn't see any effect of the lifetime. So here, non-zero versus zero lifetime almost had no effect at all. And our suspicion or our explanation again is that the electric current already relaxes at the point where you form the resonance, because already there the charge content of your system changes. Or not the content changes, but it's not carried anymore. If you have a pi plus and a pi minus, for example, going to a rho zero, then you have immediately the rho zero at that stage, and it doesn't matter if it lives for a while or not. And that's one at least the idea we had here, that for the conductivity, the lifetimes are not the major part. But there is another interesting feature, in particular, if you now go to the so-called cross conductivity. So if you have an electric field on your mixture of hadrons, you will not only influence the electric charge current, but you will also introduce, due to charged baryons, some baryon current, and you will also have some charged strange particles that can then be influenced, and you will have some strangeness currents. And we have basically now calculated all these different cross conductivities between charge and baryons and strangeness, and again compared to some analytic result here. And this is the final result for the full hadron gas for the temperature dependence of these 3 different quantities. And without going into too much detail, because time is running out, let me just mention that these conductivities, as one probably could have guessed, are very, very sensitive to the degrees of freedom in the calculation. And our idea is now, if you could calculate these coefficients on the lattice, for example, and one can then match which of these curves matches best what the lattice would predict, one can actually get some idea on the degrees of freedom of your hadron gas. And so the outlook after all what we have done so far is to go for multi-particle interactions. So I told you that we so far had only binary interactions because of detailed balance. If one wants more different possibilities, like a particle going directly, some decays should be actually like the omega 2-3 pion decay is measured. There should be a decay of the omega just 2-3 pions. But then one also wants the back reaction. And if one wants such reactions, and that is also relevant for moving to higher or denser systems with such a hadronic transport approach, one might have more particles close to each other, and they should interact. And this is what we're moving towards too. So we have now some infrastructure to calculate multi-particle interactions with the stochastic collision criterion. So on a grid, you really have these stochastic probabilities. And you have these stochastic probabilities that decide if a certain interaction is happening, and that you can easily extend to a higher number of particles, like 2, 3, 4, 5. And we're currently working on applying this to interesting physics cases, of course. And then I also would like to mention an effort that is carried out by Agnieszka Vergiluk and Volker Koch at Berkeley, but based on SMASH, where they basically improve our mean fields, or the nuclear-nucleon interaction with relativistic mean fields. And That is also important for the for the beam energy scan studies, because that basically allows to have the same equation of state with a critical point in the first order transition also in the transport approach. So if you then build a hybrid approach based on such an approach, you can actually have the same. So your hadronic transport approach knows about that equation of state, and that there was actually a critical point somewhere in the calculation. And she has been working on the vector interaction in this mean field approach to actually tune it to get different structures in the phase diagram, so you can have basically different interactions based on, and then you basically get your different dynamics based on these different mean field parameters. And I'm hoping to explore that further in the future as well with a PhD student here in Frankfurt, continuing this effort. And then the technical slide. So if you got interested and think, oh yeah, Smash could be useful also for my project, it's open and free to the public. So you can look at this webpage with all the information also about the prior publications with the code, and download the code itself here on GitHub. Looks like this roughly. You can have then here the analysis suite. This contains all these validation results, so these cross sections, comparison to a vast amount of heavy ion data at different beam energies for PT spectra, rapidity spectra, whatever you're interested in. Just check it out here. And then we have a user guide and documentation as well. And last but not least, we have now also a page with a couple of animations and nice visualizations, and even a tutorial on how to make these movies by using ParaView. So if you're interested to play with that, go ahead and use this new pages here. So now my summary is that we have been developing this new hadronic transport approach called SMASH, that we have the bulk observables in reasonable agreement with the experimenter in the GSI low energy beam energy range, where you would expect the hadronic transport approach to work. We have electromagnetic radiation incorporated, dileptons and photon production, and are studying that also from the late stage hadronic afterburner at high energies. We looked a bit into baryon stopping within this string excitation model, and then I talked a bit about the transport coefficients at low beam energies and their sensitivities to the resonance properties. And and our code is already a module in the Jetscape or Xscape framework that is developed for high energy heavy ion collisions, and we are currently moving towards multi-particle scattering and improved interfaces to the hydrodynamic evolution for a future hybrid approach. So feel free to use the approach if you have any questions. I'm happy to answer.